I want to look at a couple of examples here of redundancy and inconsistency within a 3x3 system of equations. What I'm going to do is I'm going to present to you a couple of questions to solve and interpret. I want you to pause the video, have a read of the questions, have a crack at them, and then come back and check what you've done against what I'm going to present to you here. Here you go. So just two questions for you, two systems of equations. What I want you to do is solve and interpret both of them and tell me what they mean. So, go for it. So I've got my first system of equations here. What I'm going to do is set them up in an augmented matrix and then interpret them from there. So putting them as an augmented matrix, what I end up getting is 3 minus 1, 1, 1, minus 1, 2, 3, 0, and 3 minus 1, 1, 3. What I'm going to do for this one is I'm actually going to swap these two rows around. So what I'm going to do is take row 2 and interchange it with row 1. The reason being, I'm then going to have a number here in the top left, which is a multiple of 1 or negative 1, and then I can use that to scale up or down easily to eliminate the other numbers within this column representing the x. So I'm going to then rewrite my system. My augmented matrix is negative 1, 2, 3, 0, 3 minus 1, 1, 1, and then 3 minus 1, 1, 3. Now, at this stage, we'd normally do elementary row operations to eliminate some of the values within it. But if you'll notice, the entries for the x, y, z components for both the second and third rows are the exact same. So if I were to do row 3, take away row 2, I'd then start to eliminate values here. So if I did row 3 take away row 2, I'd have negative 1, 2, 3, 0. I'd then have 3, negative 1, 1, 1. And what I'd then have for the third row is I'd have 0, 0, 0, 2. So what I've done is I've got this augmented matrix to a point where I can look at the system of equations and I can interpret them. This bottom row here implies that 0 equals 2, which cannot happen. So because of that, it's an inconsistent system of equations, which means that there's no set solution, whether it's a single solution or an infinite amount of solutions, that will satisfy these three linear equations there. So that's the interpretation. It's an inconsistent system of equations, there are no solutions to it. Second system of equations was given by these three equations here. So again, what I'm going to do is start by taking it and putting it into an augmented matrix. So it's going to be negative 3, 4, negative 6, negative 2, 1, negative 1, 2 and 1, and then 2, negative 2, 4 and 2. So that would be my augmented matrix. Now again, same logic as before. If I take these two rows and swap them, I'll have a 1 here, so it'll be easier to scale up or down to eliminate the other values associated with it. So what I'm going to do, I'm going to take these two rows and swap them. So I'm going to do row 2 swapped with row 1. Doing that, what that will then give me is a top row of 1, negative 1, 2, 1. Then negative 3, 4, negative 6, negative 2 for my second row, and then 2, negative 2, 4, and 2 for my third row. What I can now do is start to do my elementary row operations. So if I do row 2 plus 3 of row 1, that will eliminate this. And if I then do row 3, take away 2 of row 1, that will then eliminate this value here. What that then means is my augmented matrix becomes 1, negative 1, 2, 1 on the top row. That doesn't change. I've then got this row here, add 3 of that. So negative 3 plus 3 is 0. I've then got 4 plus negative 3, so 4 minus 3 gives me 1. I've then got negative 6 plus 3 times 2, so negative 6 plus 6 gives me 0 there. I've then got negative 2 plus 3, which then gives me 1. My bottom row then becomes row 3, take away 2 of row 1, so that take away that gives me 0. I've then got negative 2 minus minus 2, so negative 2 plus 2 gives me 0. I've then got 4, take away 2 2's, so 4 take away 4, which is 0. And I've then got 2, take away 2 1's, which is 0 again. So what I've got here is a system of equations where the entire bottom row is 0. So what that means is I've got a redundant system of equations. I don't have a single solution that will satisfy all of them. So what I can do is find equations for my unlimited solutions and the infinite number that I've got, relating x, y, and z to one another, and that'll give me the solutions I'm after. So what we can do is let's take z equal to z, because what that means is I've now got an infinite number of values for z that I can take. If I then look at the equation here for y, well, that tells me that y is equal to 1. And if I then look at my x, well, that'll tell me that x is equal to 1 plus y minus 2z. So if y is equal to 1 from here, that'll then tell me that x is equal to 2 minus 2z. So then, my system of equations quite simply becomes x equals 2 minus 2z. I could put over 1 if I wanted, but I would just leave it like that. I'll have y equals 1 and z equals z. So sometimes you'll see it written over 1, hence the reason I've put it there. So there you go. I've solved it and I've interpreted it. There's an infinite number of solutions. So if I were to use planes to represent these three systems of equations, what that would mean is that would be the line of intersection of all of the planes. So interpreting them, solving them, reading them off, as long as we know how the patterns of planes and the way that they intersect one another exists, when we solve these systems of equations, that is essentially what we're calculating. We're looking for solutions that work for all three of them. So again, if we represented them by planes, we'd get a geometric representation of them. So that would be how we'd interpret them.